All right, good afternoon, everyone. So we're going to continue our discussion about neural networks today. Today we're going to focus a little bit more on the training side of it. But just to review, we are looking at an approach to classification that is based on doing some sort of feature transformation that enables linear classification to work better. And the feature transformation is actually something that we will learn from the data itself. So we saw one example where we have a data set that cannot be classified well by any linear classifier because of how the data is distributed. But we could do a two-stage procedure where in the first stage, we use something like, the first stage, let's see, this is probably the best way to describe it. The first stage uses some sort of linear processing followed by some sort of nonlinearities to get some transformed features. And those transformed features then go through standard linear classifier, and we are essentially learning the transformation as well as the linear classifier parameters. And we can see that this works well. Because of the way we set it up, you can understand the first stage also as sort of a form of linear classification where each one of these rows of W and elements in B, you can think of that as like a linear classifier itself that produces some sort of score or soft probability depending on how far the sample is from the line. And then those soft probabilities, these guys, are actually the inputs to the second stage. And when we train this, we jointly learn all these different parameters, and we do that in the same way we've learned in previous units. So let's see. Sorry, I think I passed it. Okay, here it is. So the way that we train it is we use maximum likelihood. So first we have to say, well, what is the likelihood function in this case? So we're going to use logistic regression. And in logistic regression, we have this sigmoid model where Z are the linear scores. And in this, or typically they were the linear scores before. Now those scores are actually things. This thing is computed by this nonlinear network here, which we're just calling F. F is dependent on all these different parameters, which we're calling theta. And so this is the final probabilistic model, the probability that the training label is 1, given the features associated with the ith training label and the parameters is this. And so this allows us to do maximum likelihood as we always did it. So here we have the negative log likelihood function. We want to minimize that, and we just plug in this model here, and we get this equation here, which depends on this somewhat complicated function f. So today we're going to start wrestling with how to do the details of this training procedure. All right, so are there any questions so far on any of this? Okay, so let's fast forward then. Okay, so let's take a look at this maximum likelihood problem. So this is what we would like to solve, but this is one of the cases where this function is too complicated to do this minimization analytically. So instead, we're going to use gradient descent to try to solve that problem. So, and in particular, this is our overall negative log likelihood. For this, you can see I'm using this script J, or I'll just call it big J. And the big J, which is the overall cost in terms of these parameters, we're going to write it as a sum of costs for the individual training sample I. So this is like the negative log likelihood for that training sample. So then, as always, we sum it over the training samples. But now, just to do something that's going to make our lives a little bit easier, we're going to normalize this by the number of training samples. So instead of this being, typically we just had a sum, now we're just normalizing the sum so that this behaves more like an empirical average. Okay, so this slight detail that we haven't seen before. Okay, so that's what we would like to do. We'd like to minimize this with respect to theta. And we learned back in Unit 6 that we have this gradient descent algorithm that does something like this. So K is the iteration of the algorithm. And it says that our parameter guess at iteration K plus 1 is the parameter guess at iteration K minus a small positive step size times the gradient evaluated at the guess at iteration K. And so let's take a look at this. This is the main thing that we have to compute now. And so when you look at the gradient of this, because of linearity of differentiation, we can apply the gradient directly here, and that gives us this. So I've just plugged in this equation, and I've moved this gradient all the way through the sum. Right, does everybody agree with that? We can do that? Okay, so now when you look at this, you can see a little bit more explicitly how much work is involved at every gradient descent step. This shows you that you actually have to compute n different gradients, where n is the size of the training data set. Okay, so in a lot of our labs, we have relatively small training data sets, although they've been getting bigger. Like MNIST has 70,000 samples. Usually people use 50,000 of them for training, 20,000 for testing. So that's n is 50,000. That's starting to get very big, or a little bit bigger. But in practice, you find, especially with neural networks, this number n can be in the millions. So just as an example, there's this famous data set called ImageNet. We'll talk about it a little bit later. ImageNet has 14 million samples. Each one of those samples is an image, 224 by 224 pixels. So we're talking roughly, 500,000 pixels per image. 500,000 pixels per image times 14 million images is roughly 1 trillion values in the training set. And that means that at every iteration of gradient descent, you would need to touch at least 1 trillion numbers, and probably touch them in several ways because you have to compute this complicated gradient. So you can see how this gets out of control, right? And that tells us that we have to ask the question, is it really worthwhile for every gradient descent step to really compute all n of these gradients? Because every gradient could actually be expensive. The reason why this is not worthwhile is because when you think about gradient descent, and we've seen pictures like this before where we have a cost surface and we're trying to get down to this center of the cost, and maybe we start like over here. The gradient descent does not go directly towards the center, right? It starts out moving in this direction, which you can see is not the right direction to go in. We actually, if we were somehow smarter or more capable, we would go in that direction. But actually, gradient descent takes us in this direction. So given that we're not even going in the most efficient direction, should we really be spending all this time computing this sort of direction that's not even right? Right? It doesn't seem like it's worthwhile. It suggests that maybe what we can do is we can actually approximate this in a much cheaper way. And if our approximation is correct on average, that means that on average we'll be moving in the right direction, but maybe, it's always going to be a little bit off the average. There's going to be some deviation from the average. So that is actually the approach we're going to take. That's what we're going to talk about next. So computed the gradient is expensive when the number of trained samples is large. The gradient doesn't actually point directly to the minimum, so it's not really worth computing this gradient with this absolute precision here. Okay, so this is what we're going to do. We're going to use something called mini batching. The idea of a mini batch, we'll do it in a picture. Imagine this is your shuffle training set. So every one of these rows here is your data matrix, your feature matrix. Every one of these rows are the features for the data set for the ith sample. So for example, if we're talking about MNIST, we have each row is our vectorized little 28 by 28 grayscale image, right? And we would have, in the case of MNIST, we'd have, let's say, 50,000 samples. So instead of using all 50,000 samples at every gradient descent step, we're going to use a small chunk of them, maybe like on the order of 100 or something instead of 50,000. And we don't like to have structure in our data set. Like maybe MNIST is organized where it shows all the zeros and then all the ones and all the twos. We don't want to like do a gradient descent step with all zeros and later with all ones. So we're going to shuffle our data before we extract this chunk, this mini batch. So that's why these are shuffled. This is the shuffled training data set. So we've just sort of randomly shuffled all those indices. And now that it's shuffled, we can just take the first 100 and then the next 100 and then the next 100 after that, right? Because it's been shuffled. So that's the idea. Let's call the subset of indices at the tth step. We'll call that IT. So this is a set of integers. That's a subset of the numbers 1, 2, 3, all the way to n. That just contains the indices in the original unshuffled data set that I'm using in this mini batch. And then, instead of doing the average where I look at all the training samples I, now I'm only going to do the average over the I in my subset of indices. And when I do my averaging, I'm only going to divide by 1 over the size of that subset. So when you have these absolute value type symbols around a subset, that always means the size of the cardinality of the set. So this is just an average over the I in your mini batch. Okay, we're going to call this thing, define it as GT. So this is an approximation of the gradient. The true gradient would have all the indices I here, not just the ones in the mini batch. This is an approximation of that, the one we're using at step T that is based on this particular subset IT. Okay, is that idea clear? That's sort of the main idea. Rather than using the entire data set at every gradient descent step, we're using a small random subset of it.
So you're just taking like a bunch of small gradient descents?
Yeah, so well, each of our gradients, it has the same dimensions, but it's computed from far fewer quantities than the true correct gradient. Just we're using like 100 samples rather than all 50,000 when doing the sample average of these terms. Okay, yes?
Is there a way to, like for regular gradient descent at least, is there a way to compute the gradient such that it points along the correct direction?
Yes. So if, we talked about this briefly before, but let me repeat it. So if this is truly quadratic, then something called Newton's method is smart enough to go exactly in one step right to the center. If it's approximately quadratic, then Newton's method will get you close. However, Newton's method is expensive because you actually have to compute this big matrix of, like gradient terms, sort of, or matrix of partial derivatives called the Hessian, and you have to invert that Hessian. And so like the steps are really powerful, but they're very expensive to compute. So for that reason, it's not a typical tool in machine learning. Once in a while you see people using it, but it's not the standard approach. The standard approach is this mini batching idea that we're talking about here. Again, part of the reason I didn't mention it before is just one of memory. So if we're talking about, let's say, ImageNet, we said that it has roughly 1 trillion values in the data set. Like, it's really hard to store all those in memory at the same time to compute this thing. If you wanted to do something like Newton's method, you would have to build this Hessian matrix out of like those 1 trillion values. So that's just, yeah, that's hard to do. So instead, we're taking the shortcut of doing gradient descent, but actually like an approximate gradient descent, where we're using these approximations of the gradient at every iteration. And it's okay if they're not exactly pointing in the right direction. Maybe they're pointing a little bit this way or a little bit this way, because this direction is not even exactly what we want to use anyway. Okay, so that's sort of the idea here. And with this approximate gradient, finally, we just do our regular gradient descent step. And so we just use that approximate gradient for iteration t instead of the true gradient. And there's various names of this. We can call it stochastic gradient descent. It's stochastic, it's random, because we make a random selection of that subset. So in that sense, the gradient is kind of this random quantity.
Does the size of that subset stay the same in each iteration, or does that also?
In practice, it's the same for every iteration, except that there's sort of an implementation issue. So as I mentioned before, the way it's typically done in practice is you shuffle the entire data set and then you take out chunks of it. So let's just say that my mini batch size was 100. The only way to get 100, let's say that the only way to get chunks that are all equal to 100 is if the total data set size is itself divisible by 100. So if for some reason it's not, maybe the last one won't quite have 100 samples in it. It will have a little bit less, or some number less than 100. So with the exception of that, yes, they're all the same size, except for this sort of quantization issue. Yeah.
Can the indices in LIT, so do the indices, can indices repeat for different iterations that I?
Yeah, so typically the way it works is you go through, you shuffle your training data set, and then you go through and you take, let's say, the first 100, you don't reshuffle it, you take the second 100, and so on until you reach the end. And now, once you've used all your samples once, now you reshuffle it and you start over. Does that make sense? So like the first, if T is the number of mini batches in my total training data set, I will go through these T steps. In each one, I will use some different subset of samples that are in these new mini batches. But the next time I start over and I revisit all my data, it's best if I don't use exactly that same pattern of mini batches. I want to use a different random pattern of mini batches. So to do that, I can reshuffle everything, and then I take the data out in chunks again.
But the first time, every index is always in one IT.
Yeah, it's sampled without replacement is one way to put it. Versus, yeah, I don't know if that terminology makes sense.
Yeah.
Yeah. So you take out some subset of indices to make your first mini batch, and then you don't go back to any of them until you've used up all the training data samples. And eventually, you probably have to go through your data more than once, generally a bunch of times. And so the next time you revisit everything, you do another random shuffling, and then you chunk out the data again.
What's the difference between this and K4? It seems similar.
Yeah, it's similar to K-fold in terms of how you partition things. Other than that, it's pretty different than K-fold in the sense that K-fold is an approach to do cross-validation, and this is we're just trying to do training. So it's kind of different that way. We're just trying to break up the data set into smaller pieces instead of like working with it all at once, because it's generally speaking too big to hold in memory. It's not worth doing this gradient step where you use all the samples, because it's just not worth it. Okay, great. Any other questions? Okay, so the next thing to do is understand, like, is there some problem with this? Like, what is, is this going to hurt us in some way? And if so, how? So, in other words, can we justify that this is going to be an okay thing to do? So the main point I want to make here is that this gradient approximation is correct on average. In other words, it's unbiased. So the way to think about that is, if you imagine, let's just say, to be easy, let's say I'm doing this very first mini batch. So the probability that I use the very first sample in my training data set is some number, right? It's like, what's the chance that I draw that in a mini batch of size B? But the probability that I draw the second one in my original data set is exactly the same as the first. And the probability that I draw the third is exactly the same as the first and the second, right? So each one of my samples I'm drawing with equal probability. I'm treating them all the same. So as a result, when you look at what happens on average or in expectation, it's the same as using all those samples on average once. It's kind of like the probability that you use any given sample in that gradient is 1/n. And then given that you use that sample, this is how it affects the gradient. So we could write this, with a bunch of different steps conditioning on things. I don't know if that would be clear or not, but basically, maybe it's sort of intuitive that the way that we're taking the data out, because we're not favoring any particular samples in that training data set over others, when we look on average of what happens, it's the same as taking the full gradient. But that doesn't mean it's the same, it's the same on average. It's not the same for every realization. No, because the gradient itself, not the average, but this GT only uses some subset and it ignores some other subset of our training data sample, so it's actually going to be different than the gradient. It's just that on average, it's the same. Is that making sense? Can you buy that? Or are there any questions about that? That's really the whole point of this slide. So if you believe that and this is, we're conditioning on a particular theta t. So, just like for some fixed parameters, theta at iteration t, what is the average gradient? We're just saying that is the same as the true gradient. So on average, it's the same. So if you believe that, then let's look at what happens to the output of gradient descent. So in the output of gradient descent, we are producing this new theta vector, given some old one, and the equation for the new theta vector is just this, so I'm plugging that in. And now, if I'm conditioning on this, when I evaluate this expectation, we can think of this as fixed, so that gives us this, and this is linear. So finally, the expected value of GT given theta t, we said that is the gradient. So in other words, on average, our gradient descent step update is also correct. This is exactly what we would have had if we would have used the exact gradient. And so that's the same as what we get on average with this mini batch. Right, so SGD updated parameters are also correct on average. They're also unbiased. Okay, so another way to say it is that this approximate gradient equals the true gradient plus some deviation. You can think about it as a noise, like a gradient noise. And that gradient noise is on average 0, but it's there. It's pointing you in the wrong direction constantly, but on average, it's pointing you in the right direction. That's the idea. Okay, so basically, as you're doing, maybe I'll draw a little picture. So we're trying to get here. Maybe I start here. I'll start here. So the true gradient would be like this blue curve, and maybe I'll draw these individual steps. You can see this is a nice smooth curve, eventually getting me right to the minimum. But this new idea maybe instead of there, it puts you over there the first time. And then instead of taking you in the correct direction there, maybe it puts you a little bit off to this side. And then maybe a little bit off to this side and this side and this side. And maybe sometimes it goes backwards and, forwards. And so eventually what you see is that you get this sort of noisy trajectory. It eventually gets to the same place. And once it gets there, it never quite settles down. It just keeps bouncing around because it keeps getting pushed away by not having the correct gradient. So even if you're right at the minimum and the true gradient is 0, which means true gradient descent would keep you there, this stochastic gradient descent is going to bounce you off it, and you're just going to be bouncing around and around. And so this is sort of what this new approach looks like. Is that sort of clear, the picture of it? Okay, so because of this additional noise, one way to combat that is to reduce your step size. So we have the step size alpha t, and you can see alpha t multiplies the gradient. So, and essentially, over the iterations, it's kind of like you're accumulating these small gradients. So the smaller alpha t is, the smaller you use any given gradient, and the smaller you use that error. And so it takes you longer to get there, but the trajectory follows the true gradient more closely. So that's what happens. It's like instead of going quickly here, you go more slowly, but you cut down on the error. So that is usually the cost of reducing the batch size. So the smaller the batch size, the more of this error, and the more you reduce your step size so that the error is not just going crazy.
So is step size and batch size related?
Yes, that's right. So like the smaller the batch size, the smaller you should adjust your step size. Exactly. Smaller batch needs smaller alpha. So that's how all these approaches are trained. And when you try it, you find it's much more efficient than using the full gradient. Full gradient is doing like these big, heavy steps. Each one of them is not all that precise in terms of taking you to the minimum. But when you use mini batches, each step is so much faster to compute that you can compute many of them in the time it takes you to compute one single full gradient descent step. And in those many updates, even though they're not perfect, they bring you a lot closer to the solution. So it's just more efficient. Okay, so that's basically mini batch. So here's just a few details. So just in terms of notation, so we've always said we have n samples in the training data set. So now let's introduce this new notation that says we have b samples in each mini batch. Yes?
Was there any way to find like an ideal alpha size based on
It's going to be some sort of
size?
cross validation in practice. So because there's all these complicated things happening, and so generally speaking, the smaller the batch, the smaller you should reduce your step size. But exactly what's the best step size, it's hard to know. So you try like maybe a grid search over several, and you do cross validation and you see which one works the best. Okay. Okay, so we said B samples in each mini batch, and that means that the number of mini batches that you can make out of your full data set would be T, we'll call it, which is going to be N divided by B. Right? Total number of samples divided by number of samples per batch is number of batches. And this is, of course, assuming that the mini batches are not overlapping, which is how we said we're going to build them. And we said we're going to do one stochastic gradient descent update for every mini batch, which means there's going to be T updates to use all of our training samples exactly once. And this number T is known as a training epoch. So training epoch is like you go through enough mini batches to completely use all your training samples once, and then you start over with a new epoch and you go through them all again in a different random order. And you do this, and so when people talk about training networks, they often talk about the number of epochs that they trained it for. Like I used 100 epochs. I just mean I went through my epoch, my full training data set 100 times, but I did it in a mini batch way. Okay. Okay, so, and we talked about this already, but the way we do is for each epoch, we begin by randomly shuffling all of our training data indices, and then we partition the shuffled indices into T contiguous subsets. Those are these ITs. And then we use subset IT to compute the gradient and cost at stochastic gradient descent update step T. So pretty much just this picture I showed you before. Shuffle everything and then take things out in chunks. And then once you're done, you reshuffle everything and you start over. Okay, so that's how we do it in practice. Yes.
How do you make sure you're converging on something as you do more epochs?
You keep a look at a couple things. You look at your training loss. You want your training loss to go down, but you also want to look at some test data set or validation, or whatever you want to call it, and you want to monitor how that is going, because if you're experiencing overfitting, that means your training loss is going to be going down. That looks great, but then your test loss might actually be going up, and then you know that you're overfitting, and generally speaking, that's not a great thing, and so you might want to come back and try changing your model in a way that is going to reduce the overfitting. Yeah.
Is this like a non-convex optimization problem? Or is
Yeah, we said that in general, once we start doing things like this network, the cost, so if we do logistic regression on, we build our maximum likelihood cost from the logistic regression model, we know that that is convex in these parameters, but it's not going to be convex in these parameters because of these nonlinearities. So
does the stochastic method help with that?
it does indirectly. It's maybe not obvious how and why it helps, but I think, yes, it probably does in practice. Mhm. Okay, good. All right, any other questions on mini batching? All right, so that's the way we're going to train. Now let's switch gears and talk about how we compute gradients. So that is tricky because we have this big neural network that has all this stuff going on, and we have learnable parameters scattered throughout the network. We have like weights, biases. We have to train all these. So this is our stochastic gradient descent update. We essentially need to compute these quantities, or these quantities here. We need to compute the gradient of the cost with respect to the current parameters and whatever data we have in that mini batch. So this is the whole question. How do you actually compute that gradient? It's kind of tricky. And in particular, the things we need to compute for our two-layer multi-layer perceptron are the individual derivatives of the cost at iteration t. So the reason why the cost function is iteration dependent is because this cost function is looking at a particular mini batch, which uses a particular subset of our gradient, particular subset of our training data. So anyway, we have to compute the partial derivatives with respect to all the WH coefficients. Those are the hidden layer weights. That's actually a matrix. So we have, within that matrix, we have to index through the parameters with, we're using the variables L and J, like Lth row, Jth column of that matrix. Then we have these BH bias terms. That's a vector, so we index through them with L. Then we have our output. This in general is a matrix of output weights, so we index through that matrix with K and L. And then we have output biases, we index through that vector with k. So those are all the things we need to compute, and we need to figure out some organized way of doing this, because otherwise it's super complicated. Now going forward, the t, we're going to do the same thing at every batch index t. So just to make the notation a little simpler, we're going to drop all the t's, because it doesn't really come into the picture. So from now on, for the next few slides, you won't see any t's. We're just going to do the same thing no matter what t is. But we'll still have all these other indices. Okay. All right, so the first thing to talk about in terms of organizing our computations is first to just draw a picture that shows the dependency of the different variables with respect to each other. So here we have the cost on the right side. This is the final cost that we're trying to minimize training. Here you can see we have these parameters with the blue nodes. So this is our hidden weights and biases, output weights and biases. Here we have our training features and our training labels. And here's the equations that show how everything is connected together. So we know that in the first stage of our network, we take our input features, we multiply them by this WH matrix, add the BH vector, and that gives us the hidden scores. So that kind of dependency, you can see that ZH can be computed directly from XIs and the parameters WH, BH, right? So that's what this means. Next, we see that the hidden activations are computed by putting the hidden scores through this nonlinear function. So that's what this means. So you can compute the A's directly from the Z's. And then next, the output scores you can compute from the hidden activations and these other parameters. So that shows you that dependency. And finally, the cost you can get from looking at the output scores and the training labels, and that shows you that dependency. Right, so this just shows how everything is connected so that you can figure out how the variables affect each other. Okay, we're going to call this the computation graph. All right, so if you remember, like, there's some basic things we want to compute. Beyond the gradients, we want to compute, for instance, just what is the loss at that iteration, right? And so to compute the loss, you can see we actually need to do all these computations. So we have to go through what we will call the forward pass. The forward pass starts with the things we know at the beginning of the iteration, which is basically this, right? We know our data, we know our current parameters. We don't know those other variables here until we compute them. So we're just going to go through from left to right, and we're going to compute them, as we can. So the first thing we can compute is we can compute these. So we're going to do that by running this for all I in our batch. So our batch now will index from 1 through B. So for all our batch indices, we're going to compute those hidden scores. Once we have those hidden scores computed, now we can compute the hidden activations. Once we have those computed, we can compute using the parameters W0, B0, or WOBO, we can compute the hidden, or the output scores. Once those are computed, we can use the labels and compute J. Okay, so this is called the forward pass. Basically, you just start at the top and go down. Or in terms of the graph, you start to the left and you move right, computing everything. So that's the easy part. The hard part is computing the gradients. To do that, we're actually going to start at the right, and we're going to move left. And we're going to move through here and compute gradients one by one, reusing computations, and that is called the backward pass. And the backward pass is what we'll spend a while talking about, because that's the more complicated part. So just, are there any questions on anything I said so far? Is this making sense? Forward pass is pretty clear, I think. So just a comment is that we saw a couple different options in terms of building our network. We saw that you can have the Z's be the end of your network, or you can process them with some output activation function and get the A's. Just for the purposes of how we're going to present things here, we're going to assume that our network stops at the Z's, just because it's simpler. We don't have to worry about these. And we're going to use those to compute the cost. So the cost is directly computed in terms of the Z's, not the A's. And so that's how we're doing it. However, it is possible to put in one more node here, which would be the A's, and then you would just have to compute that and compute your cost based on those A's. So you can do that. You can definitely do that in PyTorch, which is how we're going to implement all this stuff in code, but it's just not how I'm doing it here in the slides. Okay, so what we're going to do next, so first, we're going to review the chain rule and try to visualize it, because the chain rule is going to be the main sort of tool we use from calculus to do these computations. Okay, so let's first of all imagine that I have three scalars, z which depends on y, and y which depends on x. And let's say I want to do dz dx. I want to know what is the derivative or gradient of z with respect to x. So by the chain rule, we know we can break up that computation into dz dy, dy dx. So visually, it's kind of like you can do dz dx in terms of dz dy times dy dx. So that's just the regular old chain rule. Here I'm stating it in terms of scalars, so hopefully that's something everyone is familiar with, comfortable with. Now, let's say that I happen to insert another variable into this processing graph. I'll call it u. There's sort of two ways to think about this. You could do the chain rule. If you want to do dz dx, you could do dz du times du dy times dy dx if you want. That's fine. Or you might say, well, there's a shortcut. Maybe I'm just going to skip over the u node. I'm going to do dz dy times dy dx. And both are fine. From the math, you can see that this term, dz du dy, this part, can just be sort of summarized as this, again, by the chain rule above, right? So the point is, even though you might have a very long computation graph, it does not mean you have to stop at every node. If you somehow have maybe this already computed, just use it. Just do this one extra little stage. Right? So you can see that our computation graph here is pretty long. So we don't necessarily want to visit every node if we don't have to. Okay. Everybody good with the second part? Okay. The third part is probably the most complicated. It's about the multivariable chain rule. So to visualize it, maybe I'll draw a couple more nodes. So in this graph, what I'm saying here is that there's actually a bunch of different variables yi, like y1, y2, y3, that are all represented here. So maybe to make the picture a little bit more explicit, I'll draw those like this, and then draw some connections like this. Okay, so we have like y1 all the way through, let's say, y4 here. Okay, so now the question is, how do I do these computations if I want to do dz dx? So, so we said if we like, we can go dz du and so on, but let's sort of like what we did above, kind of forget about u, and let's skip directly to these yi's. And so now, the way I like to think about it is that, in some sense, the information about how x affects z, it actually flows through different channels on its way to z. And we have to use all those channels. They all contribute equally, so we just have to add them up. So when we do dz dx, we can do dz dy1 times dy1 dx plus dz dy2 times dy2 dx, and so on. And that is where we get this multivariable chain rule that we've seen before, but now we're just trying to visualize it a bit better. Okay. So the key thing when we start looking at this somewhat complicated computation graph here is to be very careful. Notice that actually a lot of these nodes have a bunch of different things attached to them. So if you remember, I is the batch index. So the fact that you have a subset here, a set, is because you have one of these ZOs for every I in the batch. So in some sense, you have a bunch of nodes here, and you also have a bunch of nodes here. But what we have to be careful about is how those nodes connect. So in this case, what's important is that the first element of the batch only connects to the first element in the first, A in the batch only connects to the first Z in the batch, right? The second A connects only to the second Z. It doesn't connect to the first one because those are different batch elements. They're decoupled. The third one connects to the third and so on. Okay. On the other hand, when you think about the dependence, let's say, of BO on J, BO, which is one of these parameters, it actually affects every one of the batch elements. So in that case, the topology is different. We actually do have to use the multivariate chain rule because the information between B, O, and J actually flows through those different paths. So that's the main thing to keep in mind when we try to tackle this big computation graph in terms of computing our gradients. Okay, so, all right, any questions on our multivariable chain rule or multivariate chain rule, either one? Yes.
You said I was the batch index?
Yeah.
I thought T was the batch index.
Um,
On the slide right before it says by dropping the batch index T.
Yeah, so I think, so here, yeah, they're kind of coupled because T is like the step of, right, this is like the step of gradient descent. But as we go from one step to the next, we're actually using the next batch, right?
Yeah.
So in some sense, they're the same thing. But over here, when we think about this is all, maybe I should clarify. So we have a within the batch and across batches, right? So T is across the batches, and that's the same as gradient descent steps. And then the I here is within the batch. So yeah, maybe I should be very careful about the across versus within. Okay, good. Everybody good so far? All right, so now what I'm going to do is I'm going to go through several cases in increasing complexity. We're going to simplify everything as much as possible first to understand it in its simplest form, and then we're going to add more complexity and do it several times. So in the first time, what we're going to do is we're going to think of all variables being scalars, so no vectors, no matrices. And we're going to use a batch size of 1, so we don't even have multiple elements in our batch. So this is the simplest possible thing. In this case, you can see I just have scalars at every node, single scalar. My forward pass reduces to this. The first hidden output score is just my weight times my input feature plus my offset, my bias, my interceptor. Okay, then my activation, which is a scalar, is just putting scalar z through this nonlinearity. Then, given that hidden activation, I just multiply by WO, add BO, that gives me my output score, and my output score and my label give me my cost. So it's the simplest we can be. And now let's figure out how to do all the gradient computations. Remember, the key ones we're interested in are gradient of our cost with respect to all our parameters. So dj, dbo, dj, dwo, dj, dbh, dj, dwh. So that's what we want in the end. But you can see that there's sort of a lot of steps between some of them. So let's go step by step and break it into pieces in a very organized and tractable manner. Okay, so the first thing, we're going to start at the right and move left. So the first thing we're going to do is do dj, dzo. So to do that, how do you do that? You look to this list of relationships, and you see, oh, this is the one that relates this big J to ZO. So now if you say, well, how do I do dj dzo. That's pretty easy. It's just whatever this function is, little j. We just differentiate little j and evaluate with respect to the first argument and then evaluate it at zo. Okay, so that's this. I'll just write that derivative with a prime. The exact form of this, I can't say because it really depends what we were using as a cost. We could be using a quadratic, we could be using logistic, we could be using a bunch of stuff. So it's just going to be some function j that depends on our task, like whether doing classification, regression, whatever. But it's whatever it is, it's something we know, and we can just do this derivative. Notice that we know the value of zo because in the forward pass, it's something we computed. So we can reuse that in this backward pass. All right, so we have dj dzo. Next thing is dj dah. This is the next gradient we want to compute. And by the chain rule, we can do dj dzo times dzo dah. Right, that's what the chain rule says. Conveniently, dj dzo is something we already computed. So that is something we computed. We just plug that number in. The only thing new to do right now is to figure out this dzo dah, this one. To figure that out, we look through our list of relationships and we see, oh, it's this one. And now dzo dah is easy, right? What is it? WO, right? So this is just nothing more than WO. And WO is a known parameter because it's just like it's the value of WO at the beginning of this gradient descent step. Okay, so now we know this. The next thing we can do is dj dzh. So for that, we can do dj dah times dah dzh. Notice that I skipped over this because it doesn't really help me. I know this, so I can just use that and multiply by this new thing that I need to figure out. So that is dah dzh. So for that, this is the relationship that determines that. And if I want to do dah dzh, that's just whatever this function is, I just have to take the derivative of that, evaluate it at zh. And so I'll call that h prime. It depends, the exact function will depend whether I'm using a sigmoid, a tanh, or a ReLU, right? It's just whatever I'm using for my activation. I know how to differentiate that, and I'll just use that at that step. Okay, and at this point, we have we know all these things here, and now we can evaluate the gradient with respect to the parameters. Any questions on this? Okay, so now I want to do dj dbo. So you can see I can do that by dj dzo times dzo dbo. That's this equation. dj dzo is something I already computed, so that is just a number I plug in. And now dz dbo, I can figure that out from this relationship, and we can see that that derivative is just 1. Next, I want to do dj dwo. For that, I do dj dzo times dzo dwo. Again, this dj dzo, something we computed before, we plug that in. Now we just have to figure out dzo dwo. That is determined from this equation, and dzo dwo is just going to be ah, right? So that's that number, that's something we evaluated in our forward pass, so we can plug that value in. So the point is that we're never wasting computations. We're always computing something once and then just plugging that in anytime that appears later. So we're being as efficient as possible. Everybody with me so far? Okay. The last step is dj dbh. So here we since we know dj dzh, we can use that and multiply that times dzh dbh. Like here. Oh, sorry. Here. So this is our dzh. We can just plug that in. And this last term, here we go, dz dbh. Can determine that from over here. That's just 1. So that's easy. And finally, dj dzh dzh dwh. Get that, and dzh dwh. From here, that's just x. Okay, so we've basically moved from right to left, and we went through all these branches and we used all these computations over again. And at the end of the day, we have computed the gradients that we need to do our gradient descent update. We do the update, then we're going to have new weights and biases, and then we start over. We do a new forward pass with our new weights and biases. We compute this, then this, then this, then this, and then we begin our next backward pass where we go backwards and compute our gradients. Another gradient descent step, and we start over. So we go back and forth, back and forth. And even though this is a complicated set of relationships, we broke it down step by step in a way that, no matter what this computation graph looks like, it could even have a different structure, different topology, we would know how to do this because it's just a very organized procedure. Right? And so when we talk about these deep learning frameworks, like you've heard of PyTorch and TensorFlow and so on, what they do is they do all this stuff under the hood for you. They figure out the computation graph, and because it's such a regular problem, they can just efficiently, no matter what it looks like, they can just efficiently do all this stuff without you ever having to worry about it. But of course, I want you to understand it, not just rely on the tools. That's why I'm teaching you about it, and that's why you'll have homeworks about it and midterm exam questions and all that. But that's basically the approach. So I think we're out of time for today, but next time we'll go a little deeper and we'll say what happens when we have a bigger batch size, what happens when we have vector variables and all that. And things will be a little more complicated with the notation, but the ideas are the same. All right, so have a great weekend. We'll see you guys on Monday.
Okay.